So as with other properties of coordination compounds, the magnetic properties are going to depend on the number of unpaired electrons in a metal complex. So you're probably familiar with the fact that iron is magnetic. The metals that we think of as magnetic are iron 3 and manganese 2 plus. Copper 2 plus is also, it has some magnetism, but it's not as strong as the other two. And we'll look at their electron configurations to understand why. Things that are not magnetic, you know that calcium is not magnetic, and zinc is another example of something that's not magnetic. So what we think of, or what we know as the macroscopic property of magnetism, is actually paramagnetism. So if we look at zinc 2 plus, which is not magnetic, and we compare it to manganese 2 plus, can you write out the electron configurations of these? Assume that they're in an octahedral complex. So how many d electrons does zinc 2 plus have? 10. So this is a d10 metal ion, and if you put the electrons in the 5d orbitals, it means that all of them are paired. For manganese, what is the d electron configuration, or the d electron count for manganese plus 2? It's d5. So for a high spin d5 manganese plus 2 complex, you have all unpaired electrons. And this kind of a complex would be paramagnetic. So these are the things that are magnetic and not magnetic, and it comes from their property of being either diamagnetic or paramagnetic. Calcium, again, is not magnetic. What's its d electron count? 2 plus calcium. It's in the second column. Yeah, it's 0. And what about iron 3 plus? It's another 5. And I'm going to write copper over here too. So copper 2 plus is magnetic, but it's not as magnetic as manganese or iron. And it's because it's a D9 and it only has one unpaired electron. But all of these things they do have some magnetic properties, and it's because these are paramagnetic. And these things are not magnetic because they're diamagnetic. I'm sure you've seen these terms before, but let me just define them for you. A diamagnetic compound has all paired electrons, and it's repelled by a magnetic field. Paramagnetic compounds have unpaired electrons. They don't all have to be unpaired, but they have some number of unpaired electrons, and they are attracted to a magnetic field. The way that we measure magnetism, there are many different ways to measure magnetism, but the most simple and common method is the Goy method. Basically, you take a little stand and you suspend by a string a tube with the sample. So your sample's in here. And it's simply suspended by a string. And then there is a magnet. And a lot of the times it's an electromagnet, but it doesn't have to be. So this is a magnet, and under the magnet, you put a balance. So you basically weigh the magnet, and then you put the sample in the magnetic field, and then weigh it again. And so things that are paramagnetic will make the magnet seem lighter because the magnet's attracted to the sample, so it will actually lighten the magnet, and that's because they attract the magnet. A diamagnetic sample will actually because it repels the sample, it actually makes the magnet heavier, or appear heavier. This method is called the Goy method of measuring magnetism. Magnetism is often discussed as a magnetic moment, but this thing measures something else. It measures something we call the magnetic susceptibility, and it's represented by X or chi. So that's the symbol for the magnetic susceptibility. And it's just basically whether the sample is susceptible to a magnetic field. So if you would get, it would be odd for you to get absolutely no change in the mass of the magnet. So something is usually either paramagnetic or diamagnetic. But the magnetic susceptibility takes into account a lot of different things. So let me just write the formula here. The magnetic susceptibility is related to the magnetic moment by this equation. And I'm not concerned with you knowing this equation. This mu effective, or this mu, is the magnetic moment. And we're going to be talking about the magnetic moment most often. So the magnetic moment is really, it tells you something about the number of unpaired electrons. And then this magnetic susceptibility here is what you measure using the Goy method. So X is magnetic susceptibility. And this magnetic susceptibility is the thing that's measured, and it's dependent on the temperature. So T is temperature in Kelvin. And this is given in units of Bohr magnetons, yeah. And those are, so 1 Bohr magneton is equal to 9.27 times 10 to the negative 24 joules per Telsa. Yeah, these are the units. This Bohr magneton is the unit. I'll give you an example in a moment to show you how you use that unit. So even though you measure the magnetic susceptibility, often the magnetic moment is the thing that's reported. So you can kind of just forget about that equation unless you need it in the future. So in past years, we've actually done a lab that we measure magnetic susceptibility. There's a balance over there in the advanced lab. It's like on the far end of the wall. It's this thing that sits on the floor, and it looks kind of like that sketch I drew. So it's like a kind of a tannish magnet that comes up to here, and then you put a sample down in it. So it's over there. You can look at it. But I don't think, since we're not running the advanced lab, I don't think that you guys will ever use it. But it's pretty straightforward. It's kind of a fun experiment. Now, the things that we're going to be talking about more in this class, in terms of S and L, those quantum numbers that we talked about last time, which was basically the sum of all of the spins and the sum of all of the angular momentum quantum numbers. You can define the magnetic moment of S and L as G times the square root of S times S plus 1 plus 1/4 the L and L plus 1. So in this equation, G is something called the gyromagnetic ratio. And for our purposes, we usually just talk about one free electron. So for a free electron, G is equal to 2.0023. And for most of our purposes, we simply just estimate G as 2. But that's where it comes from. S, of course, is the spin quantum number, the sum of the spins, and L is the sum of the angular momentum quantum numbers. So for this magnetic moment here, so notice that there is a spin component. So this is whether or not you have unpaired electrons or how many unpaired electrons you have. And it also depends on which orbitals those electrons are occupying. But for most purposes, so in fact, for most of the first row transition metals, the magnetic moment depends mostly on the spin. And so we can say that the spin-only magnetic moment is a good estimate of what the magnetic moment would be. So we call this mu effective, or the spin-only magnetic moment, and it would be G, which I'm going to estimate as 2, times the square root of S times S plus 1, and then you would give that in units of Bohr magnetons. And it's just simply Bohr magnetons. Another way to write this, I'm not going to use this today, but it's just as good to do this based on the number of unpaired electrons, And if the number of unpaired electrons is n, you can use this equation. So I'm going to write, for first row transition metals, the magnetic moment matches well with the spin-only contribution. So that's for most of the cases. When they don't, when the measured mu does not match well with the spin-only mu, then that means that this assumption was not correct and that there is going to be more contribution from the angular momentum than we had expected. That's all that means. So let's look at an example. I'd like you to estimate the spin-only magnetic moment for an iron 2+ high-spin complex. So what's the d electron count? So if it's high spin, that means that there's a small delta. So I would fill in all of the orbitals first before pairing. And that means I have 4 unpaired electrons. So my big S is equal to what? So what the m sub s spin quantum number for any one electron is what? When I talk about spins, what do we usually talk about? What is the quantity that we give a spin? 1/2 or -1/2, right? By convention, we usually just use the 1/2, and so the spin here would be 4 times 1/2. So it's just, I just would use 4 halves or 2. Okay, so then the mu effective is equal to the gyromagnetic constant, which I'm just going to estimate as 2. So the mu effective here is the g times the spin 2 times 2 plus 1. So that ends up giving you about 2 times the square root of 6. And then if you did this in your calculator, you would find that this was 4.89, and then you just put the units as Bohr magnetons. So another common problem is to be given the magnetic moment and asked to determine what the electron configuration looks like. So here's another example. The magnetic moment of hexaaqua iron 3 is 5.9 Bohr magnetons. Is it high spin or low spin? So in other words, they're asking you to calculate the number of unpaired electrons. So what's the d electron count of iron 3+? We have a d5. Now, there's 2 approaches to this. You could say, okay, mu effective is equal to 5.9 Bohr magnetons, and this is equal to 2 times s plus 1, and solve for s. But if you do this, you're going to have to use the quadratic equation. And I hate using the quadratic equation, so I would not approach it this way. Instead, I would just say, okay, well, a high spin looks like this. There's 5 unpaired electrons. So I would say, what is my calculated mu effective for 5 unpaired electrons? And it would be 2 times 5 halves times 5 halves plus 1. And I would find that that was equal to 5.91 Bohr magnetons. And then a low spin, D5, would look like this. And there's only 1 unpaired electron. So I would calculate my mu effective is equal to the case where S is 1/2 because there's only 1 unpaired electron. And if you calculate this, it gives you a mu effective of 1.73. So quite obviously, the closest case then is a pretty good, this calculation is a pretty good estimate for the high spin case, and it matches very well with the measured value of 5.9, right? So this is a high spin. And that matches with what we know about water's position in the spectrochemical series, right? Anytime you have a first order transition metal with water as your ligand, anything weaker field than water is going to be high spin. Anything stronger field than water is usually low spin. So let's do another one. So an octahedral cobalt-2 has a Bohr magnet, or has a measured magnetic moment of 4 Bohr magnetons. What's the electron configuration? What's the first thing you need to know to solve this problem? Tell me, what is the d electron count of cobalt 2+? Good. It's D7. So this is a D7. If you have high spin, you have 3 unpaired electrons, so your capital S is 3/2. And this ends up giving you a mu effective of 3.87 Bohr magnetons. So that's not exactly 4. See what the low spin case is? So in the low spin case, you have 1 unpaired electron. That's just like in low spin iron or hexaqua iron 3. So in this case, you would get a Bohr magneton of 1.73 again. Now, in this case, your measured magnetic moment does not match either of these directly, but it's closer to the high spin case. And so it's easier to see that it's basically on the other side of this range. So this would be consistent with a high spin, but there is significant departure from the calculated value because of an angular momentum contribution. Okay, in this case, again, I want you to tell me if this is high spin or low spin. What would you guess just based on the spectrochemical series? Yeah, why did you guess that? It's a strong field ligand. It's going to increase that delta, right? Did you know that by memorizing the ligands or like in the spectrochemical series, or is there something about cyanide that gave you? So cyanide, it's negatively charged, right? But what is it about cyanide that tells you it's a strong field ligand? It has pi bonding, so it has pi bonds on the atom. So either one of these atoms could technically donate. Most of the time the carbon is the one that's directly coordinated, but either one of those atoms, if they donate, those atoms have pi bonds. And that means that they have pi star orbitals. So they can accept metal d electrons into their pi star orbitals, and this is a pi acceptor ligand. So when you have pi acceptor ligands, they're strong field, which means they increase delta. And so you would end up getting a low spin. Yeah, because it's strong field. So if we look at so strong field means that there's a big delta. So this is strong field, and then weak field means that there's a small delta, right? And so the strong field, you pair the electrons. What did we say this was? This is D5 again. So you pair the electrons first, and so it's a low spin. Yeah, so low and strong are kind of opposites, right? And so it's hard to correlate them. So you have to understand what it means. The language of chemistry is the most confusing part, I think. In the weak field case, now you're putting them in separate orbitals before you're pairing them. And so the weak field case is the high spin. Okay. So which one is it? Based on so we said it's probably the strong field low spin case because of the cyanide ions, but let's make sure that the magnetic moment is consistent with that. So if you had a magnetic moment over here for this, this one has 1 unpaired electron, so your calculated spin-only magnetic moment would be 1.73 Bohr magnetons, just like it was up here and in the case before. In the high spin case, we already calculated that. It's 5.91 Bohr magnetons. L is the sum of, so if we number these 2, 1, 0.
Oh, okay.
Yeah, so you have to you basically add up the m sub L values of the orbitals that are occupied. Yes. And if there's 2 electrons, you add twice. So the big ML value for this particular case would be 2 plus 2 plus 1 plus 1 plus 0. So it would be 4, 5, 6 in this case. Okay? And that is not the ground state configuration of just this free metal ion, right? It's different. So when we were calculating the m sub L value before, when we were finding the ground state term, we always were maximizing that m sub L value. But we were doing it for degenerate orbitals, which means that you put them all, so it would be more like this case over here. Where in this case, your ML value would be 2, 3, 0, minus 2. So it would be 0. Yeah. Okay. So, anybody knows that the measured magnetic moment does not match well with either one of the cases? What? Okay. You notice that L must be contributing, right? So this is a case where the spin-only assumption is not working well. You can see that it's a little bit closer to the low spin case than it is to the high spin case if you're just kind of estimating, but it's still not a very good calculation, and that's because of the angular momentum. There's a couple cases, and D7 is one of them, that are typically not very good when it comes to assuming that the spin-only case is accurate. But this is the type of analysis you would do. So if you were given the magnetic moment, you can calculate the spin-only magnetic moments and see if you can make predictions on the electron configuration based on that. And if you can't, that's probably because there's an angular momentum component that's significant. Okay, I'm going to briefly talk about cooperative magnetism, but I'd like you to, for your own good, I'd like you to read section 20.8, and that's where this really talks about cooperative magnetism. So it turns out that magnetic properties of materials depend on the electron configuration of the metal ions, but also on other components of the crystal structure. So what kind of ligands are there? How close are the metal ions to each other? And it also depends on temperature. The most important thing to understand from this reading is the different types of magnetic materials. There's two main types. There's ferromagnetic and antiferromagnetic. A ferromagnetic material will have the spin, so if each one of these arrows represents the total spin magnetic moment for one metal ion. So if you have a crystal or a solid where all of your spins are able to align, you increase the net magnetic moment of the material. This is a cooperative effect, and it's called ferromagnetism. Most of the things that we think of as magnets are ferromagnetic, and they're usually iron with some kind of an oxygen ligand. These are very common for metals with unpaired spins in the d and f orbitals. The other type of magnetic, or the cooperative magnetism that you can see, is antiferromagnetism. And this is a case where you have spins that are coupled. So if you have one metal ion with a spin going in one direction, another metal will align its spin anti-parallel to that magnetic moment. So you will have a situation where spins are coupled, and this is called antiferromagnetic coupling, where spins are going in opposite directions. And this is caused most often by coupling through bridging ligands. You're coupling the electron spins through ligands. So if you have two metal ions that are near each other, and I'm going to draw a sketch of one of their d orbitals, and we could say that this was the x squared minus y squared orbital on each metal ion that contains an unpaired electron spin. So I'm going to write that with a red arrow. So there's an electron in each of these guys. So in a ferromagnetic material, spins would be aligned. In antiferromagnetic material, they're opposite. So what normally happens is you have a ligand in between. Let's say that ligand has a p orbital. Oops, and I should change my drawing. Hold on. I'm going to change this so that it matches, so that my symmetry makes sense. So I'm going to redraw my x squared minus y squared orbital. Like that. And then I can draw. So this ligand basically has a p orbital that's bridging between the two metals. So what will happen is the ligand will have two electrons in its orbitals, and they will actually couple from one metal to the other. So one of the electrons will couple to that metal, the other electron will be, so one will be down, one will be up, and then the other metal will couple. And what that gives you is that the two metals are antiferromagnetically coupled. These two different types of materials have different temperature profiles, so some of them become more magnetic when you heat them up. Some Some of them become less magnetic. As long as you understand the difference between these two, you'll be okay. But it's interesting, especially if you're in engineering and you'll ever work with magnetic materials, it might be good for you to read that section.